Okay, we're going to analyze some graphs today. And so we're going to be looking at graphs and um, noticing where they increase or decrease and things like that. And I realize that we're looking at just random graphs. They're not connected to real life data. And so sometimes it seems silly, some of the things that we're doing, like who cares where this graph is increasing or decreasing? But and that's really an issue, right? But with math, we so many times learn the skill first so that in the higher maths, like calculus, we've got the skills that allows us to do things that are really connected to real life. So bear with me because we need this skill to help us out next year if and when you take calculus. All right, so when I look at this graph, I have to remember we read graphs left to right. We are always reading from the left to the right. And so as I read left to right, I see that the graph is increasing, right, for this part, right? And for this part, once again, I am not on my smartboard, so I'm just using my finger on the touchpad. So forgive me for that. All right, and so we want to describe where it's increasing. And so we have to have an agreement, and this is super important. Everywhere all over the world, there is this agreement that when we are analyzing a graph and describing increasing and decreasing, we are using the numbers from the x-axis for our answer. So we're looking at the x-axis and we're saying, almost like this. Imagine that there's a little, oh gosh, I can't draw it, right? But let's say there's a little camera here, and it's a rolling camera. It's on wheels. Okay, it's on wheels, and not only is it a rolling camera on wheels, it is a movie camera, and it is filming the action. And so it can only roll back and forth on the x-axis. And so let's say it's filming the action as the graph increases, and it wants to know, hey, director, where do I start? Well, unfortunately for this little movie camera, it's going to have to start at what? Negative infinity, right? Because that's where really, if we go keep looking, the action is starting at negative infinity, and it works its way up. And then let's see if I can move this little thing. Oh, I can. This is exciting. And so where is this movie camera going to stop? Well, it's going to stop at -2 because it's going to look up and go, wait a minute. After -2, if I keep rolling, I'm going to look up at the graph and I'm going to see it's starting to decrease. Okay, and we don't want to include that. And then the director's like, wait a minute, the action increases, the graph increases in two different places. So ready, let's start shooting in second place. So the camera quickly notices that, well, if we start here at 0 and keep going, it's increasing, it's increasing. Unfortunately for the camera, right, it's going to have to keep going because even though we can't see it, we know there's an arrow, right? There's going to be an arrow right here. No arrow implies that there is an arrow. And so, long story short, we're going to describe this increasing in two different intervals, from negative infinity to -2. And let's remind ourselves, an and is an upside down U, and from 0 to infinity. And you may be wondering, wait a minute, Ms. Overby, why do we use an or when we're talking about domain and now an and when we're doing this? Well, think about it. Domain describes what x could be. X can either be included in one interval or another interval. A number can't be, let's say, both from negative infinity to -2 and from 0 to infinity. No, a number, an x value, would only be included in one of those intervals. So we use or when we're talking about domain or range. But with this, where is the graph? We're not talking about x anymore. We're talking about where is the graph increasing? It's increasing in two intervals, right? In the first one and in the second one. So we're always going to use and when we talk about increasing and decreasing. All right, so let's say that the director is no longer looking at where things increase and instead is looking at where does this graph decrease. So we're going to be looking at from here to here. All right, and this is where it gets a little tricky because our brains want to say, oh, it started at 4 and it ended at 0. And we have to say, no, 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 we're not talking about the height. We're not doing range. We are just a little movie camera, right? And we're documenting on the x-axis where the graph is decreasing. Remember, we always use, let's see if I can get my little yellow pencil back. We always are using the numbers from the x-axis. Students, for some reason, have a hard time remembering this. So let's see, where's the movie camera going to start its action? Well, at -2, because it looks up and the action is just starting to decrease, right? From -2 all the way to, that was me screeching hold, 0. So decreasing is from -2 to 0. Now, I bet you're wondering, are we ever going to use brackets? No, we're not. Well, we could at constant. Okay, that's another story. But for increasing and decreasing, really when you think about it, when you're at this height right up here, right where x is equal to -2, we're not decreasing at that time. The decreasing starts right after that, right as we move down. So we're going to be using parentheses always when we increase and decrease. And you may want to stop the video and write these important things down. They're important. All right, constant. Constant just means, is there any part of the graph where it's not increasing and decreasing? Nope. So we're going to put not applicable, or we could put undefined. All right, I am going to copy my little camera. I know it doesn't look like a camera, but in my mind, it is. All right, so let's see what the next one holds. All right, let's get the camera back. All right, bring the camera down here, and let's see. It's asking for where does the graph increase, and at least we can see it's only increasing in one spot, right? That increase starts at 0, and then we're going to film the action. Oh man, that arrow means our camera's going to be going on. Yep, boop, hits a wall, but it really does go on to infinity. So the graph is increasing from when x is equal to 0 all the way to x is equal to infinity. All right, decreasing. Once again, we're going to start where the action starts. So the lowest place, the lowest number where the action starts is -3. And the camera would film the action and then come to a screeching halt right at 0. So our decreasing is going to be from -3 to 0. Okay, the constant, remember, we always start intervals with the lower number. So that arrow right here means our camera is going to have to start way back at -infinity and go and go and go on the x-axis until it stops at -3. Let's see if I use brackets. I didn't. I used parentheses. So we'll see if Delta Math uses brackets or parentheses for constant, and we'll talk about that. It makes sense. We couldn't use brackets for -infinity, so we would always use parentheses there. But for constant, when we come to screeching halt at -3, it really still is constant there. We could have used a bracket, but we'll see how Delta Math does it, and we'll adjust accordingly. Okay, now let's switch to, a lot of times we want to look at graphs and say, hey, where's their max or where's their min? And really we talk about relative max, relative min, and absolute max and absolute min when we get to calculus. And right now we're just going to be looking at this and going, hey, I see that my lowest point right here is at 2, 0. So I would say my maximum occurs at the point 2, not 2, 0, at the point 2 comma 1, and here this quadratic that is upside down, my max. Did I say max over there? Because I'll tell you what, it's the morning and I'm not sure. The min, this is the absolute min, but we can just say min occurs at the point 2 comma 1, and here is the max, the tallest point occurs at -3, 4, and you did that last year, right? We're just revisiting that. And a lot of times we want to look at a graph and say, hey, that graph is even, or that graph is odd. And so I think you touched on this a little bit last year in 2Trig, but let's revisit it. So this graph is considered even because f of -x equals f of x. Another way to put that is, instead of looking at this as being x, let's say this point right here is 2. Okay, I could have picked like a 1. That could have been easier to draw, right? And so this one would be -2, and we notice it doesn't matter whether we're looking at x is 2 or x is -2, they both have the same height. Let's say this means that the y in this case would be 4. So regardless of whether we had a 2 or a -2, For this graph, they have the same value for the function where the y is equal to 4. When that happens, we say that a graph is even. It doesn't matter what x we pick. Let's say we pick, x is 3. Well, for x is negative 3, it's still going to have the same height, the same y value, the same value for the function. And when that happens, we say a graph is even. So what happens when the opposite happens? Let's say we're looking at, and once again, we'll look at, instead of x, we'll say a 2. Let's say we're looking at what x is equal to. And let's say that in this case, it's 1, 2, 3, right? The y value is 3. Well, then we could look at, hey, I wonder what happens when x is equal to negative 2. And we'd see, when x is equal to negative 2, the answer isn't 3, but there's still something special going on here. The answer is negative 3. Okay, the cost of not going into school and doing my videos on my smartboard is that you guys have to look at these numbers that I'm trying to do, just using the touchpad, so forgive me. All right, so here we go. When this happens, when we look at an x and see that the height is a positive 3, but then when we look at the negative of that x, so instead of 2, we're looking at negative 2, we notice the height is exactly the opposite, right? It's the negative of the other height. When this happens in a graph, we say that it's odd. I don't know if I said this. I'm going to go back real quickly. Even graphs are always symmetrical with respect to the y-axis. And so here with odd graphs, they're always symmetrical with respect to the origin. And I know that's a weird thing because if looking at the graph, that dotted pink line explains what I'm talking about. There's not true symmetry like with the y-axis. With the y-axis here, if we would have folded the graph over the y-axis, the graph would have laid right on top of itself. Here it's a different kind of symmetry because certainly if we fold it over the pink dotted line, we are not going to get where the graph matches up on each other, but you can see there's a type of symmetry over this dotted pink line, and that's what we're referring to. Okay, and sometimes there's just no symmetry. More often than not, we're going to say the graph is neither because there's no relationship. We can't fold it over the y-axis, and there's not a relationship if we did a dotted pink line through the origin. And we'd say, this graph, it's nice and everything, but it's neither even or odd. All right, so I wanted to look at even and odd parent functions so that you could see that there's a pattern that's going on. I'm going to tell you that this y equals x is going to be odd, y equals x to the third is going to be odd, and that y equals x squared is going to be even, and y equals x to the fourth is going to be even. And so you're like, oh, I see what you're talking about, Miss Overby. So maybe we could make this rule that when we're looking at a parent function that's raised to a degree, a power, we're going to say when that degree is even, then the parent function is even, and when that degree is odd, then the parent function is odd, and that's true, and that's just for parent functions. You gotta be really careful because as soon as we say f of x equals x squared plus 4, well, actually, we'll be okay with that. But if we say f of x equals x minus 4 in parentheses raised to the second power, that's not going to be even anymore. So we're just talking about parent functions. And I know it's a surprise for those of you that have not graphed parent functions with different even powers. You may want to have fun and pause the video right now. Go to Desmos.com, and that's what I did real quickly. And you can see the red graph shows what the graph y equals x squared is, and the blue graph shows what the function y equals x to the fourth. And so if you're wondering, yes, y equals x to the 6th, y equals x to the 8th will both have the same, all the way up till, the highest even number you can think of, will have that same pattern where it's, the graph to the left is going up, the graph to the right is going up, and it will be even. It didn't do the odd functions, sorry, but if you want to do that, you could pause and do the Desmos odd functions. But sometimes we're going to be asked to just look at an equation and tell us whether, or tell somebody whether it's even or it's odd. And we could graph it, but we also need to know how to do it algebraically. And so what I do is this. I realized that the definition of an even function is where f of negative x equals f of x. And some teachers teach, oh, just plug in negative x and see what it gives you, and then plug in x and see what it gives you. Instead, I like using 2 and negative 2. It's just more concrete, right? So what I'm going to do is I'm going to look first at this function, and I'm going to plug in 2 for x. So f of x, right, is just saying the function at a certain value of x. So f of 2 says I'm going to find the value of the function when x is equal to 2. And I'm just going to do that by plugging in 2 for every x. So when I see x to the fourth, I'm like, okay, 2 to the fourth, which is going to be, 16, right? 2 times 2 is 4 times 2 is 8 times 2 is 16. 16 minus 2 is 14. All right, so the drum roll is going to be, what happens when we plug negative 2 in for x? Will it be even or will it be odd? Let's see. Oh, it's neither, okay? That was really anticlimactic. Now, if it were even, we would have gotten the same answer. We would have said, hey, if f of 2 is equal to 14, then f of negative 2 is also equal to 14. We could have had a happy ending, would have been even. But in this case, we're going to say, no, it's neither, okay? Let's look at what I have behind here. All right, this is the graph of x to the fourth minus x, and obviously this little funky thing right down here means we're not going to have any kind of symmetry. All right, let's look at example 2. Let's go ahead and use this new way to find if it's even or odd by plugging in a 2. So the first thing I'm going to do is say, okay, let's plug in a 2, and I get 2 over, that little slash refers to a fraction, over 2 squared plus 1. So 2 squared plus 1 is 4. 4 plus 1 is 5, so we get 2 over 5. All right, please, please be even or odd. I don't want another neither. So this time we're going to do the same thing. We're going to plug negative 2 in, and we'll see what we get. So when we plug negative 2 in, something special happens. We don't quite get the same answer, but we get the negative of the answer. See how 2/5 and negative 2/5 are the exact opposite of each other? When that happens, we say we have an odd function. And we view that that's what we focused on the graph. Oops. But an odd function happens when we plug in the 2 and the negative 2, or the x and the negative x, and we get opposite answers, 3 and negative 3. So same thing happens when we're doing it algebraically. Whoops. All right, let's see what we had here. So when we plug in the 2 and the negative 2, and we get answers that are almost the same, but just have one has a negative and one doesn't, we say, yes, it's odd. And if we look at the graph, we can see that this would have symmetry over with respect to the origin, which is like taking that little pink dotted line through the origin with respect to the function and the origin. All right, that's it. Hopefully that helped. Rewatch it if you have questions, and I'll see you in class.